to discuss today is the geometry of a sequence of graphs. So these are called diamond graphs. So I'll introduce all the objects and all the notions that I'm going to look at today. Some of them have been already introduced by Kwame this morning or in the previous talk, but feel free to ask any questions. Okay, something is not clear. All right. So the sequence of diamond graphs. So the first graph in the sequence. So you just start with the 4 cycle like this. Okay. So you can think of this as the 4 cycle. I think of this as a K22, as a bipartite graph. Okay, so you have 4 vertices, 4 edges, and then at the second step, so what you do, so this is a fractal construction. Okay, so you start with a copy of your first graph. Okay, then you remove the edges, and you're gonna replace every edge by a copy of D1. Okay, so you get something like this. Okay, so this is D2. And then you keep doing this. Okay, so I'm not even going to attempt to draw D3, but so you take a copy of this guy, you replace every edge with a copy of D1, and you keep iterating. Okay, so this is a fractal construction. So what you get is a sequence of graphs. Okay, so these graphs are finite. Okay, and when I have a sequence of graphs, I always think of them also as metric spaces, because every graph you can put the shortest path distance. Okay, so you take 2 vertices in your graph, you count the number of edges of a path between, of course, connected graphs between these 2 points, and then you look at the shortest path, and it gives you the distance between the points. Okay, so when I talk about the metric about a graph, it's going to be the shortest path metric. Okay. So you have this sequence of diamond graphs, and so they've been actually extremely important for many people, in particular in computer science, because they realized that the sequence of graphs was very relevant to the dimension reduction into L1. Okay, so that's a completely different topic. I can tell you more if you want to talk. But the point is that we're trying to understand how well we can embed a sequence of graph into other metric spaces, and in particular into certain Banach spaces. Okay? So now you need to quantify how well. Okay, what it means how well. Okay, so one of the notions that is really well studied is what is called the N distortion of a metric space. So N and M are 2 metric spaces here. Okay, and what I'm looking at is so I'm looking at the infimum of the D, the constant D, such that there exists some scaling factor S, some map F from N into N, and such that so for every pair of points in the domain space, so you have this inequality here. X equals Y. This is going to be S times D, the distance between X and Y. Okay, so here this is going to be the distance in M, the distance in M, and the distance in M. Okay, so it's a like multiplicative notion of distortion. Okay, so and so you can try, of course. So here my metric spaces are finite, so there's always an embedding into any metric space that had enough points to contain them. Okay, so now of course the theory becomes quantitative. Okay, if you have an infinite graph, just to understand if this is finite or not is already an issue. So, and so there is this nice result of Johnson and Lee and Schechtman. This is around 2009. So they proved the following metric characterization of a local property of Banach spaces. So they show that, so X here is going to be a Banach space. So if a Banach space, so I'm going to explain what it means. So this means that if it has an equivalent norm that is uniformly convex, so this was already more or less defined in Poincaré, but I'll go back to this in a moment. So this can be characterized in terms of this metric invariant here, So you can look at the X distortion of the diamond graph decay. This gives you a number, okay? And what they said is that, well, this has to go to infinity when K grows. Okay, and it's an if and only if statement. Right? Now, on the right-hand side here of the equivalence, what you have is a purely metric statement. It's about Bi-Lipschitz embedding. Bi-Lipschitz embedding, here, you're only looking at the metric structure of your Banach space. Okay? It does not involve at all the linear structure. While on the left-hand side, you have a local property of Banach space. So property, which essentially is, you can read it on finite dimensional subspaces, and it's isomorphic and so on. Okay? So, so X is uniformly convex. So let me just recall briefly the definition. So if delta X of T is positive for every T, where this is defined as the following. So this is moduli. So you're computing the distance between the unit sphere to the midpoint. And what you want is that the normal X normal Y is less than 1. And these 2 points are at least T of 1. Okay. So this is a notion of curvature of your unit ball of your Banach space. Okay. So this example, so it's not the first characterization. So this class also, when we mentioned, so this is the same class as the class of superreflexive Banach spaces. Okay. So it's not the first purely metric characterization of superreflexivity because Bourgain was the first one to prove such a metric characterization. Now, in terms of a different sequence of graph, the sequence of binary trees. Okay. Okay. So now this is one example of a result in the Ribe program, if you've heard about it. So, because there is this beautiful rigidity result of Ribe, which says that if you have two Banach spaces, and if they are uniformly homomorphic, so if they look the same as metric spaces, then they are crudely finitely representable in each other. So, which means that they have essentially the same finite dimensional subspaces. Okay. So this suggests that you should be able to reformulate local properties of Banach spaces in terms of purely metric statements. Okay. And so this has a theoretical interest, but also a practical interest because you're developing notions that make sense in metric spaces and not only in Banach spaces. And now this can be applied in a variety of settings. Okay. So now, so of course there is a quantification of the notion of uniform convexity. So we're going to say that so you can look at the modulus of uniform convexity and look at the situation when the modulus of uniform convexity is of power type Q. Okay, so here I'm hiding some universal constant, doesn't matter. And so you can actually write this in terms of a homogeneous inequality. So this is equivalent to the following. So for every pair of points in your Banach space, so what you have is that. So I'm going to rewrite an inequality that was in the cornerstone. Okay. So, well, one implication, which is if you have this homogeneous inequality, then you have power type is essentially trivial. Okay. So the difficulty is to show that if you have this power type estimate, then you have this homogeneous inequality. Okay. And this was done by both Kalton and Lieb, I mean, at least with sharp constants. And so Banach spaces that are like this, we call them Q uniformly convex. Okay. Okay, and so for us, it's going to be very important to look at these homogeneous inequalities. Okay. So these inequalities, so of course, what I didn't write is that there exists a constant positive such that you have. Okay. So these inequalities, they're very sensitive to renorming. Okay, But when you iterate them in a certain way, then you get inequalities that are isomorphic invariant. So for instance, you can iterate this inequality here to get the notion of martingale cotype Q that Guanya already introduced this morning. Okay? And the notion of martingale cotype Q, it's an isomorphic invariant. Right? And so what PCA proved, so beautiful renorming theory, it's 76. He proved that the class of Banach spaces admitting an equivalent norm that is uniformly convex, you can write this, so that's one way to put it, as this union here, okay? So, which means that every Banach space has an equivalent that is uniformly convex, has an equivalent norm that is Q uniformly convex. Okay. So again, one direction is trivial, but now the other one is not. Okay. So and this class here is equivalent to having martingale cotype Q. Okay. So his renorming theory is based on these martingale inequalities. Any questions so far? All right. So now the question, so there is a natural question here, is you have this metric characterization of Johnson and Schechtman here, for this class here, but now you can somehow stratify this class into these subclasses, and now you can fix Q and say, okay, do I have a metric characterization of this class here, right? And so this was resolved, and actually I want to make a remark before I talk about this. The remark is that if your Banach space X is Q uniformly convex, so here, you see in this characterization, there's two directions, right? There is an embeddability direction, so if you're not super reflexive, you need to embed the diamond graphs into every non-super reflexive space with uniformly bounded distortion. But if you're uniformly convex, you want to show that this quantity goes to infinity, and actually you want to understand how fast maybe it goes to infinity. So if your space has this bar type behavior for the uniform convexity, then what is known is that this goes to like this. So k to the 1 over q. Okay. So this was already so this was already shown by Bill and Gideon in their paper, but there is also another argument of Lee and Naor for in the range Q. I mean for Banach space for LP spaces between 1 and 2, for instance, 1 is 2. But the argument of Bill and Gideon, it's actually a very neat argument. It's a self-improvement argument. It says that if you have an embedding of, let's say, d2 to the k, okay, with some distortion into a uniformly convex Banach space, then actually you have an embedding of d2 to the k minus 1 with a better distortion. Okay, so you can show this, and then when you keep iterating, then at some point there is some distortion that pops up. Okay, so their argument though is very Bi-Lipschitz. Okay, you cannot say anything about weaker notion of embeddings with this type of argument. Okay. So now, what about the characterization of the class of Banach spaces emitting an equivalent norm which is Q uniformly convex? So this was resolved, well, first using the geometry of trees, but there is another solution which is more recent. So now you fix Q. Now you fix Q bigger than 2 in this case. And so you can show that, so this is due to Alexandros Eskenazis, Mendel, and Naor, that this is true if the Banach space is diamond Q convex. Okay. So what is diamond Q convexity? So I'm not going to write the inequality. Okay. So, but this is a metric invariant. Okay. So it's a Poincaré type inequality. Okay. So you're comparing, let's say, distances between edges in the diamond graphs with distances between a pair of midpoints. Okay? And so it makes sense in metric spaces. So it's so there is nothing about the linear structure here. Okay? And so they have this solution. All right. Okay. So now maybe another remark that I want to make is the following. So these are two different types of metric characterization, and this is really a pattern in the Ribe problem. So when you have these classes, let's say that there is no quantitative parameter attached to it, and you have this metric characterization in terms of impossibility of embeddability of sequence of graphs. Okay? But when you quantify things, then you have this metric invariance in terms of the Poincaré type inequality, and this Poincaré type inequality captures the geometry of the graphs, okay, of the sequence of graphs. Okay, so one remark is that now if you have a metric space which is diagonally convex, okay, because I said this makes sense in a metric space. So what you have is that you can say the following thing. So you have this integral here. So the integral of a function rho. So here, when the whole sequence, so rho embed into F. So what do I mean by rho embed? Maybe I should go back here. So by rho embed, I mean that. So let's say there is a 10. So for every so there exists a map from dk into your metric space, okay? And here, instead of this estimate here, you have an estimate like this, okay? For some function rho, okay? That is independent of k. Okay?
But all of them are Lipschitz with the same function.
Yeah. Okay. So you will have this y. And then let's say you have some uniform constant here. Okay? So let's say 1 Lipschitz or 100 Lipschitz, doesn't matter. Okay? But then you have this function rho here that controls the lower boundary. Okay? And this function rho, I mean, it doesn't have to be a linear map because then there would be a Bi-Lipschitz embedding, so it could be something much weaker. And usually we want this to go to infinity when the distance goes to infinity. And this is a type of coarse embeddings. So when you have this Poincaré type inequality, okay, then you have this control here. You can show that this control. Okay, so this was first observed by Romain Tessera, but not for the diamond graph, but for the binary trees. Okay, so we refined a little bit this Poincaré type inequality of Bourgain to get this bond, because Romain is a geometric group theorist. He was interested in binary trees, but infinite height. And of course, he wanted to understand how this graph coarsely embeds into Banach spaces. Okay. So here, this means that the function t over log t, some exponent will. Okay. All right. So this is really like one example of a result in the Ribe program. Okay, so which is a very developed program. And now what I want to switch gear, and I want to talk about similar problems, but for different properties and different sequences of graphs. Okay. So
this remark, is this just one-sided implication, or there is a chance for the other side?
No, okay. So for trees, the analog for trees, it's tight. You can show that it's tight. Okay, Because for every function somehow that satisfies this, you have an embedding. For diamonds, I don't know. I don't know. I mean, this is something that you look at, but yeah.
For trees, it's tight?
Yes.
So you take the best possible Q and
well, I mean, for instance, into LP, let's say you're in a Q and you take a function that satisfies more or less this, then you will be able to find an embedding with this compression.
Okay, but to specific spaces, not to a general.
No. I mean, there are examples where it's tight. Yeah. I don't know in general. Probably not.
Sorry, maybe I missed it. Did you actually define what is diamond Q convex?
No, not yet.
Implications.
Not yet. So then I will get back to this.
Not this property?
No. I'll get back to this notion. Okay. I will actually write a curvature-like inequality from which you can iterate it and get the metric invariant. Okay, but I'm gonna try to avoid writing the inequality because it's a sophisticated inequality. But I'll explain the intuition. Okay. So today I'm just trying to explain the intuition behind these arguments. Okay. All right. So now what you can do is, of course, here I'm looking at the two branching diamonds, right? Because I have these 2 points here, and then I have 2 midpoints. But I can also look at 3 branching, 4 branching, or k branching diamonds. I mean, or branching diamonds. Okay? Does it make any difference here? Actually, it doesn't make any difference because the characterization, I mean, here, Johnson and Schechtman, is the same if instead of 2 branching, you take or branching. Finite, I mean, arbitrary large, but finite. Okay? So this was shown by Beata, Hangiana, Antonina, and Mihail Ostrowski. So, of course, the prime was not the non-embeddability, the prime was to embed this diamond graph with high branching number. And it was not trivial to extend the embedding to this case. Okay. But what I'm interested in is if instead of finitely branching, I look at countably branching diamond graphs. Okay. So this is going to be my first graph. So I have countably many midpoints here. So now already I have an infinite graph to start off with. And then, I'll need to omega the same construction. Thing is I have countably many midpoints here, but also here, right? It's impossible to draw, but that's what I have. And I can study the geometry of these graphs as well. Okay. Now, this is not going to be related to local property of Banach spaces, okay. But it's going to be related actually to asymptotic property of Banach spaces. And what we were able to prove, so a couple of people got involved here. So myself, Ryan Kossi, Steve Dilworth, Lenka Kusarova, Thomas Schumprecht, Laurent Ribani, and Sheng Zheng. Okay, so this is 2016. So what we prove is the following. So now if you have a Banach space, and the Banach space is reflexive, so I'm assuming that the Banach space is a reflexive Banach space. And an additional condition, which is called asymptotic unconditional structure. Okay, so whatever it means. So we prove the following. So the Banach space admits an equivalent norm that is asymptotically uniformly convex. If and only if, well, you have essentially the same characterization here. So, but now in terms of the countably branching diamond graphs. Okay. So it looks very similar. Yes.
So I have a question about the previous dimension. So you said that if you change the diamond of the first by a diamond with more branches, it does not change. But what if you replace it by any finite graph? Does it also not change?
So what do you want to do for?
Like I want to say that instead of having that initial graph, I pick any finite graph. Does it change?
Oh, any finite graph?
Yeah.
Well, I mean, to do this construction, first you need to start with an ST graph, okay, that has a top and bottom, so that you can replace everything. So you can look at different types of graphs here and iterate, you would get the same characterization. Okay, like Laxo graphs, where instead of starting with a diamond, you add a handle here on top at the bottom. So I mean, there's a fairly general class of graphs that are called slash products of graph that will give you the same characterization. Okay, but then if you take a completely different graph, then they will be completely different. Okay, but it can be generalized. It can be generalized to more general slash products of graphs. Okay, but you need to be able to do this subfractal construction. Right? Okay, so maybe I want to keep this. Maybe okay, so what is the Banach space that is asymptotically uniformly convex? Okay, so X is asymptotically uniformly convex if it's a similar condition. Okay, so you have a modulus and you want your modulus to be positive for every t. But so what is the modulus? So the modulus is defined as follows. Right, it's a little bit more complicated. So it's a combination of in and suit. So what you're looking at is this quantity here. Okay, so you have two vectors, you have t, and here, so x is going to be an element in the unit sphere. Here you're going to take a sup. So this is a finite codimensional subspace, closed finite codimensional subspace. Okay. And then you take the int into over the unit sphere of y. Okay. All right. So I mean, you can try to compare this modulus to this one. That doesn't look the same, right? But in fact, you can show that if you're uniformly convex, then you are asymptotically uniformly convex. Okay. So you can compare, and you do this by comparing the y-graph. Right? So, but why asymptotic? The asymptotic comes from here. So here you're allowed to throw away some finite dimensional subspaces. Right? Take a finite codimensional subspace and then look at this quantity there. Right? So maybe the best way to understand the difference is look at this space here. So take an LP sum of n infinity n's. Right? So is this space uniformly convex? No. Right? Because it has trivial cotype. It contains the n infinity n's. Right? But this space here is asymptotically uniformly convex. Okay? So I mean P finite. Okay? So which means that this modulus allows you to forget about these finite pieces here. Okay? You don't forget about all of them, but you forget about this one here. So in a sense, it says that the intuition is that this modulus only looks at finite dimensional spaces, but that are realized in a very specific way, in an asymptotic way. Okay? And these guys, for instance, they're not. Okay? So this one behaves pretty much like LP from the asymptotic point of view. And this is very easy. I mean, like if you try to prove that this is asymptotically uniformly convex, I mean, it's really a Leiden-Hemp argument. Right? So
the sup in your formula is over what?
So the set of finite codimensional subspaces. Okay. Right. Okay. And now you can see the diamond graphs. They're finite graphs, right? So every finite metric space embeds into an infinity of the right dimension. Right? So this guy here contains the two branching or the finitely branching diamond graphs isometrically. Okay. But now, of course, the question is, does it contain the countably branching diamond graphs? The answer is no. So you have a difference between this finite object and this countably infinite object. Right? So to prove this, well, the non-embeddability direction, we actually use the similar argument of the Johnson and Schechtman argument, okay, which is the self-improvement argument. So this works very well in this case. So that was not the hardest part. And again, so we're going to say that, so here this is a remark. So if delta x of q is a core type q, so now the range of q is between 1 and infinity. Okay, it's not like in the local case where it has to be at least 2. This is between 1 and infinity. So if we have this, then you have the same order of rules. Okay, k to the 1 over q. Okay. So the number of points here is essentially 4 to the k. Okay, so this is log of the coordinate of the space to the 1 over q. All right, but the argument here, the self-improvement argument, doesn't tell you anything about this weaker, like coarse embeddings, okay, these row embeddings. So if you want to say something stronger, you will need some metric invariant. Okay, that's going to be the point of the end of the talk to discuss this. And of course, the question is, well, is there a quantification here? Okay, and well, this is due to Mendel, which was fresh. Probably around, well, around 2000. They show that so a similar result. Okay. So you also have this stratification. Okay. So if you have a AUC norm, you can always find an equivalent norm that is QAUC in this sense, that it has port type Q. Okay. So the PZ renorming theory in the local setting has been worked out in the asymptotic setting using an approach which is you're looking at weakener trees and estimates on the branches. Okay. So the theory in the asymptotic setting is a little bit more difficult because the duality doesn't work as well, unless you're in the reflexive case and so on, but it's been worked out. Okay. So now the natural question is, well, can we do what Eskenazis, Mendel, and Naor did? And I'm going to try to explain to you what can be done. Are there any questions so far? Okay. So now let me go back to this notion of diamond convexity. Okay. So I'm going to go back. So what's the approach to show that if a Banach space is Q uniformly convex, then it is diamondly convex? So the approach is one approach is the following. So if your Banach space is Q uniformly convex, then you can show that that X satisfies the Q, so what is called short diagonal inequality for uniform convexity. Okay. So I'm going to write what this inequality is. Okay, so this is a curvature-like inequality, and once you have this, okay. So let me write already what it is. So what is this inequality here? So it means that there exists some constant k, and now it's an inequality that makes sense in a metric space. Okay, so I'm just going to write the inequality with a metric. Okay, and this satisfying this inequality means that it satisfies this inequality for the metric induced by the norm. Okay, so that for every omega x y z. So now I'm going to write this in the metric space. So you have the following inequality. So the distance between omega y cube, then 1 over t cube, So this is less than Q. 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 And here, I take a uniform average of this. Okay. So if you've never seen this inequality, I mean, you might need a little moment to process it, right? So, but what it says that, so you have omega x, y, z, right? So think of these points in this configuration, in the diamond configuration. So here what we're comparing, so here you have the distance between omega and y. So one diagonal, this is going to be the other diagonal, and here you're taking the average of distances between edges. Okay? So in what Banach spaces is this clearly true? You've seen that already. In a Hilbert space. Hilbert space, if you look at the parallelogram identity, I mean, if you work it out a little bit, you will get this. Okay? So, of course, the distance takes the norm, the difference between vectors.
Q is equal to 2.
With Q equals to 2, yes. And the constant, actually, we actually have constant 2. Okay? And this is also true in metric spaces of non-positive curvature. Okay? And actually, when Q, so that's why I call this a curvature-like inequality, because when Q equals 2 and K equals 2, this is the quadrilateral inequality, which actually characterize non-positive curvature in the sense of Alexander group. Okay? So if you Q uniformly convex, which means that, now forget about this, think about this inequality here. From this inequality, it's not too difficult to derive this one here. You just apply it twice, average, and then you get this. So you have this linear homogeneous inequality, and you derive this purely metric inequality. Okay, so this is step 1. And then, step 2, what you do is you iterate. And then you get time and Q convexity. So again, I'm not going to write what it is, but because there are several versions, but and it's not important to understand the philosophy of what I'm trying to convey here. Okay. Okay, so you have this. And actually every space for which we know that the space is diamond convex, it's by proving this. Okay. Essentially. Almost, you have more examples where you don't prove this. But for the most part, okay? So really, you need to focus on this curvature inequality here. Okay? And I'm doing it time. So now you want examples of spaces satisfying the Q short diagonal inequality for uniform convexity. So you have Banach spaces, Q uniformly convex. You have metric spaces of non-positive curvature. Okay, so for instance, trees. And so now it's a little bit tangential to what I'm trying to explain to you today, but I cannot refrain myself from mentioning this result. So if you have a Banach space that is Q uniformly convex, okay, then what you can do is to form the Heisenberg group over this Banach space. Okay, so I don't want to go into the detail of the construction, but I mean, if you know the Heisenberg construction, I mean, it's similar. Okay, so you have to twist a little bit the addition to make it non-commutative. So what you need here is a anti-symmetric bilinear form. Okay, but okay, you can define what is a Heisenberg group over an infinite-dimensional Banach space or any Banach space. And this space so satisfies the 2Q short diagonal inequality for uniform convexity. Okay. So here you need to raise the exponent by 2. Okay. So now this gives you a pretty nice class of metric spaces. Okay.
What is the matrix in this?
So the metric here, so on this, so I mean, so the geometers, they would use the Carnot-Caradot metric, okay, the CC metric. But for us, we're using this, Corani type norms, okay, that gives you a translation invariant metric, which is equivalent to the CC metric. So I don't work with the CC metric. I just work with Corani type norm. Okay, I see them as a metric spaces, not really as a Banach group or anything like that. Okay. And the idea, so what's the idea here? The idea is to realize that the Q-uniform convexity inequality here is equivalent to this one here. So for every AB, okay, so again, there is some constant. So you have AQ plus A minus BQ over 2. So this is going to be okay. So this homogeneous inequality here is actually equivalent to this one. With different constant maybe, but okay. So I mean this is really a triviality in the Banach space setting. Now, and what we do here is that, so Chris in the previous paper was the first one to realize that actually this inequality is relevant for the Heisenberg geometry. We prove an analog of this inequality here for a certain Corani type norm. And once you have this one here, you can still derive, I mean, this, okay, which is clear in the Banach space setting because they're equivalent, but actually in the Heisenberg group setting, I mean, things go wrong because of the way the addition is defined, okay? And because of the dilations that do not behave like dilation in Banach spaces, okay? So here there's really a tricky computation with this one, okay? All right. So now what I want to explain to you, and how much time do I have left?
17 minutes.
17? Oh, good. Okay. So I want to explain to you what we can do in the asymptotic setting. Okay? Or, I mean, the steps here, the corresponding steps in the asymptotic setting. And the idea is to look at things from a probabilistic perspective. Okay? So what's the problem if we want to prove, let's say, some analog of this Q-short diagonal inequality for uniform convexity, but instead of a two-branching diamond, for a countably branching diamond? You can see the problem, right? Because here, you're taking a uniform average over the 4 edges. When you have a countably branching diamond, you have infinitely countably many edges. So forget about uniform averages. Okay? So this is a problem. And there's all kinds of problems. So when we look with Chris, we look at a similar problem for another inequality, which is called the Q-fork inequality, which is related to the geometry of binary trees. Okay? And what we said is, so we used heuristics and we said, well, if we cannot take uniform averages, we're going to take suprema or infima and see what we can do with that, okay? Because the problem is at some point you need to iterate these inequalities. And when you iterate, I mean, things can go wrong, right? So, and what's amazing is that these inequalities, they're quite robust, okay? So you can take infima, suprema, and get a weaker inequality, you can still iterate it, and then you still get the metric invariant that's usually sufficient to give you the distortion lower bound, or the bounds on the compression function, okay? And of course here, you can do the same thing, and then you will get somewhere, okay? So you will be able to prove some metric invariant. But the thing is, I mean, I was really satisfied with this, and I wanted more like a conceptual way to understand, because it felt too much like a guessing game. Okay, I can do this, great, but then it didn't feel like the right inequalities, for instance. And so the idea is to look at the probabilistic perspective, because in this result, so where you reformulate asymptotic properties of Banach spaces, okay? So this program, I mean, it's a asymptotic variation of the Ribe program. So now we call it the Kalton program, because like Kalton has had a huge influence on getting this metric reformulation of asymptotic properties. And the techniques are very different, okay? In the Ribe program, you have a lot of harmonic analysis, probability theory, while in the asymptotic setting, it's more like infinite combinatorics or Ramsey theory, okay? But there's no probability, okay? And I actually want to bring back the probabilistic intuition in the picture and try to understand how these programs are related, because there's definitely analogies, but there's discrepancies as well. And I want to understand them from a conceptual level, okay? And since most of you here are very interested in probabilities, I think that would be a good thing to show you here. So I'm carrying this project with my student, Luis Aceves, and also Audrey Fauvert from Granada. And so this, what I'm going to talk about, is part of what we're going to look at with Luis right now. It's still an ongoing project. So, okay. So what's the probabilistic perspective here? So if you look at the Q uniform convexity inequality, this is an inequality about pair of points, right? But you can look at it from a probabilistic angle. And so you can reformulate. So it looks like it's maybe useless to do that, but you will see that I'll try to convince you that it's not. So your Q uniform is convex if, so there is the constant, such that for every point in the space, for every function on this one-dimensional Q, with the following condition. So you want its average to be 0, where mu, so it's the uniform probability measure on this field. So you have this. So here it's going to be so Q. Here. So you can rewrite it like that. And this, just a moment of thought, will tell you that, yes, this is the same thing. Just introducing some probability statement here, right? And then actually, so now this is a non-trivial result. I mean, this is due to a ball, and then it was again reinvestigated by Mendel and Naor. This is equivalent to the following. So for every map that is bounded, so it's a bounded sequence. For every U probability measure of n, okay, so you have this. Okay. So you can also show that uniform convexity is equivalent to that. Okay. And so what's behind here is the notion of Q-barycentric metric spaces. Okay. So I'm not sure if I will have time to get to this. But okay, so now you go from this this 2-point inequality to a statement like this. And now, so this is the local part. Now, in the asymptotic part, so if I have a reflexive space, okay, so what you can show is that so the modulus of asymptotic uniform convexity is of power type, because right now I haven't shown you any homogeneous inequality that characterize this, right? So if and only if, so there is some constant, so that for every map here, and for every u, so u is going to be an ultrafilter on n, what you have is the following. Okay. So, n. Okay, so, and then unique. Okay. So you can show that. So now you probably start seeing the analogy, right? So you have expectation on one side, and here you have, so this is the weak limit along the ultrafilter U. Okay. But this is in fact a probabilistic statement, but for a different probability theory. Because there is this well-known probabilistic interpretation of ultrafilter. So if you have an ultrafilter on N or anything, so an ultrafilter is just a collection of subsets, okay, with stable and rotating superset intersection. And if you're an ultrafilter, every set is either in the ultrafilter or not. So it tells you if a set is big or not. Okay? So when you have an ultrafilter, you can associate a 0, 1 value. So this is a Boolean value, finitely additive probability measure. Okay? By just saying that mu of A equals 1 if A is in the ultrafilter, and 0 if A is not. Okay? So you have a probabilistic interpretation. This is one more. But for us, it's actually crucial here, because what you can do is you can define, if you have, so I'm going to call a Boolean valued finitely additive probability measure an ultra probability. Okay? So if you have an ultra probability, and if you have a bounded function here on n, and define on n to your reflexive line space, you can just define, so this is the definition, you can always define this because of weak compactness of bounded sets in reflexive spaces. This is well defined. So in your reflexive spaces, you have this non-standard theory of probability. Okay, and and this is exactly the same statement as this one, but just in two different probabilistic settings. And once you realize this, it's amazing all the doors that it opens. Okay? And so maybe 3 more minutes. So let me see. So okay. So I'll keep this. Okay. So now what you can do is, now the analogy is really at the conceptual level. Now I'm not using heuristics anymore. I'm looking at the same notion in two different probabilistic settings. And what I can do is the following. So here, yeah, okay, so here, I didn't mention that, but so this you can show that a Q-uniform convex space is Q barycentric, and barycentric essentially meaning that it satisfies this inequality here. to some translation. And this is a notion that makes sense in a metric setting. Okay? And you can show that Q-bicentric implies this inequality. So in the asymptotic setting, we can now this is a probabilistic statement. And I can transfer this probabilistic statement, standard probability statement, into my non-standard setting and come up with what we call Q-tricentric. Okay, I'm not sure I'm going to have time to write the definition here. And then, well, we can show that if X is reflexive plus QAUC, well, this gives you an example of an intracentric space. And this implies some inequality here. So let's call it a Q short diagonal inequality for nearly uniform convexity. That's for the sake of this talk. Okay, and I'm going to write the inequality. Okay. And so this inequality says the following thing. So again, there is a constant such that for every error point, for every function here, so this notion is going to make sense in a metric space. I'm going to write the notion in the metric space. So you have this and between omega and 1 here. So you see it's similar. So now here you have an integral of this is by I j. So now here I'm looking at the product, the probability j. And here I have an average of, and this is going to be the expectation of distance between omega and phi q plus the expectation distance between y phi q. So what is the product here that you put? Because I mean these are ultra probabilities. So I need to have the right product for ultra filters. So it's the Fubini product. I mean it's called Fubini product for a reason. Right? So if you have a ultrafilter on two ultrafilter on ends, you can define the Fubini product. And what it says is that when you integrate, I mean when you take limit, you take limit in a certain order. Okay, so it's associative, but it's not commutative necessarily. This can create problems, for instance, in this setting. And so you have this inequality here, and now, of course, I mean this is not an inequality that you come up with if you just use heuristics, right? If you just use heuristics, you get some weaker inequality, which would be this one here, or something similar. So here you take the integral of ij, and here you would take just suprema and maxima. So you would get this and the suprema over I. So you would get like some much weaker inequality here, where you have like suprema on the right hand side and infima on the left hand side. Okay. And this one you can prove it directly to go from here to here. Okay. So forget about if I tell you to prove this implication here, you don't have to think probabilistically. Okay. And this invariant here, you can actually, yeah, so I'm just going to say one word. You can iterate this invariant here. It's fine. You get a metric invariant. This metric invariant gives you the distortion lower bounds, but also the estimates on the compression function, something that was not achievable with previous techniques, the self-improvement argument. Okay. But of course, the main thing is how to iterate this one, the strongest one, if you think about the renorming problem and everything. Okay. Now the difference between here and here, so this one here, I can write this in a probabilistic way. And what you have here is uniform averages. Okay. So here you can think of this one as an average, a uniform average of a uniform average, two nested averages, right? But here, the nested averages Now you have a combination of a uniform standard average with a non-standard average. And this causes trouble. And this explains somehow why the asymptotic theory is different, but also sometimes where it's similar, because we're looking at the same inequalities, just in two different probabilistic settings. Okay, and one is weaker than the other somehow. So I think, truly believe there is potential to bring the probabilistic intuition back. And I think it's probably a good platform to start. Thank you.